Hello. Yeah, good evening. Is my screen visible?
Yes, sir.
Okay. So we shall start with like week five live session. Hmm. So of this course, Introduction to Fluid Mechanics. So today we will be solving topics related to assignment four. Uh, so this is mostly this topic deals with hydrostatic pressure. So fluid in statics itself. It mostly deals with pressure. So we have covered slightly like this topic slightly in the previous lecture as well. So today we will solve some more problems related to this. So let's see what's question number one here. So question number one here like states that on a plane surface the hydrostatic forces uh, form a system of parallel forces. We often need to determine the magnitude of the force and its point of application. So it is asking what is the point of application called. So, so let's first try to understand what the question is trying to say. So on a plane surface, so we have a plane surface. So what is a plane surface? Like this basically means that all the points on this lies on the same plane. So it's not there is no curvature in it. It lies on the same plane. Now hydrostatic forces form a system of parallel forces on this. So we know, if it is inside a fluid, like if we take the surface, then there will be pressure acting normally inwards on this surface, right? We will have pressure. Pressure as force per unit area. So this is like the normal stress, the averaged out normal stresses that we will have in case of static fluids. This is just hydrostatic pressure. So we will have that acting all over the surface. Now, what we want to do is here find the magnitude of this force and its point of application. So this can be represented. So we have if we have the same surface and only one force might be acting on it, hmm, uh, then if this can be represented like this, like it has the same effects, then what is this particular point called? That is the question. Hmm. So how can I replace a distribution of force into one point force? So this is a distribution of force, right? Like every point, certain amount of stress is acting on it, and uh, we if we take the cumulative add up all these small forces which are acting on each of these small areas, then we will get a net force, and this F is basically the net force. But this net force can be acting anywhere because like these are all parallel forces, they all have the same direction, the same general direction, which is like in here in this problem is this direction. So like anywhere if this force acts, it should give us the same amount of force, right? But here we are not interested in that. We are interested uh, we are also interested in the since it's an extended surface. We are also interested in the rotational effects, and there is only a very particular point where if this force acts, the whole surface will like the whole surface will have the same effect rotationally as well. Like if I take the moment from this point, then the moment across the surface will be zero, right? That is actually the meaning of this, the point of application of this force. Because like if this point, if I move this force somewhere else, if I move this force somewhere else and take this point, then there will be uh, some moment associated with this because of the distance away where this force is being applied. So uh, are you on like understanding what I'm trying to say?
Yes, sir.
Hmm. So for having a particular point of application of a force, we must, at that particular point of application of the force, the moment must be zero. So the force will be the total addition of all forces, and the point must be such that the point of application must be such that all these extended forces of pressure will have moment zero on this particular point. So let's say like we have means if it is not an extended surface, we have line. So this might be like a 2D, a two-dimensional simplification of this. So when I'm saying a line, it actually might be a plane. So we are seeing it from such a direction that we are assuming it to be a line, and we are also assuming that in the other dimension that is not represented here, which will be like outside the plane of the screen or inside the plane of the screen. In that particular direction, there is no variation. So if we do that assumption, we can say like this pressure is a function of x. So some variation, like varying pressure, is being applied on this plate. Now, how do I find a particular point which is point of application? Let's say I'm calling that x4. So how do I find this? First of all, the resultant force that is acting on this uh, on this plate on at the point x, so let, let us call that f. So this f we can find as integration. So let this be from 0 to L. This is the length of this plate. So integration from 0 to L px dx. Hmm. So if it were area, I would have written just dA or dx dy to integrate over both the surfaces. But here in this case, we are just taking like it has a unit width, and we are ignoring the other dimension. So this is just for simplification purposes. So like this, we can find out the force. Hmm. And now, how to find out x0? How to find out x0? So x0, we will use that particular concept where there is no moment across this x0. So, uh, like force for every point is px into dx. This will be the force. Hmm. Now, what will be the moment? In the moment there will be this term associated as well. Hmm. So x minus x0. This is the distance from which, like for example, this pressure is acting on some dx small element. So, and this is some distance away from this. So we are taking this as x minus x0. So this will be x minus x0. So integration from that 0 to L, this will be 0. If we solve this, then we can get this x0. So I'm going to the next page. I'm going to the next page and I'm writing this down. I'm writing this down again. Uh, so, so integration px x minus x0 dx. This is equal to 0. Okay. So what I am doing? This is a moment balance equation. At the point of application of these forces, uh, the moment is 0. Now here x0 will be constant while x varies with x is basically the variable here. So I can simply change this as 0 to L. Whatever the variation of pressure is there, this is fine. X dx. While I am taking this on the other side, so this will be x0 integration px dx. Now what is this? This I know. This I know. This I have just now calculated as the resultant force, right? So this is F into X0. So F into X0. So F into X0, this is equal to integration P of X dx. Hmm. This also like you can also try to understand in this way. So it may be like from the point zero, you are trying to calculate the moment on this particular plate. Then what will be the moment? Since the resultant force is x, resultant force is f, and the resultant point of application is x0. The moment will be f into x0, right? And also you can calculate the moment using integration. So you take a small element, and a force on that small element is px dx, and the distance from this 0 is x into px dx, and I will be integrating this over the whole length. So that is exactly what is the second term. So if you just take moment balance against at any point of this particular plate or like surface, then this you will get the x0. So this is like an easier method to calculate this x0. Now what is this x0? That is the question. What is this x0 called? So I am giving you this mathematical introduction because this will be helpful in solving like further problems. Hmm. Because you will need to find out where this point of application is there. Like if a certain variation of pressure acts on a particular surface, then where the point of application is there. For that, you need to have this concept. So what is this point of application called? Can you tell me? So
Yes, sir. Center of pressure.
center of pressure. That's correct. So we are dealing with the pressure here. So definitely not center of gravity. There is no relation with gravity here. If we are talking about surface forces, there is no relation with meta center as well, and also no relation with center of buoyancy. It is center of pressure, and that's the answer that is given. So we will use this concept of center of pressure, and that the like a distributed pressure acting on a particular surface can be reduced to a single force and acting on a very single point. So that concept we will use to solve more problems. So let's go to the second problem. So this is an assertion reasoning type of problem. So we have two statements here. One is that bottom part of dams are subjected to larger. Okay, so there is first a statement. Dams are built much thicker at the bottom. So you can like if you have visited any dam site, you will know this. Like, it is generally there is a very um, um, comparatively much narrower portion is at the top, and at the bottom it is like much larger. It is holding water this side, and here some like land area is there. So generally most dam sites have this kind of construction, and also like where their opening is there, the gate is there. Then there is a gate at the bottom, so it, uh, canals are connected here, so that when the water is released, there will be flow through the canals. So, however, like wherever you see, you will find that the bottom part is much thicker compared to the top part. So, both these statements are related to this. So, the bottom part of dams are subject to larger forces, and pressure force increases with depth. So, are both these statements correct?
Yes, sir. Both the
Hmm.
statements are.
Both the statements are definitely correct. So bottom part of the dams are subjected to larger forces, and pressure force increases with height. And this is also true. Like R is the correct explanation of A. So we know, like, from the free surface, this is the free surface where atmospheric pressure is acting. So however deep we go, like this H, how whenever the H increases, the pressure will increase. So at the bottom, the pressure, like it is much farther away from the free surface, much farther away from the atmospheric pressure. So the pressure due to the water level above that particular point is much higher. So as we go down, the pressure increases. So this pressure increases, and thus the bottom parts of the dams are subject to larger force. So this explains this statement. So the first answer is correct here. This is called tapering of the dam. This is a tapered shape. Like you may have heard tapering in your design course in mechanical studying that. Okay. Yeah. So question three. So here, okay, this is also like from a a conceptual question rather than a numeric. So here, an engineer is tasked with estimating the hydrostatic forces on a submerged horizontal flat plate. He correctly predicted the hydrostatic force acting on the top surface of this plate as Fr. So it is given that hydrostatic forces on a horizontal plate, hmm, uh, submerged horizontal flat plate, it is given as Fr. So the resultant, this is the resultant force. And now he is in a dilemma when the plate is rotating around the vertical axis, passing through the centroid. The hydrostatic force acting on the surface of this plate in the later scenario will be. So how much, if this plate rotates, how much will be the hydrostatic pressure? That's what is asked. So first of all, if it is a horizontal plate, what will be the variation of pressure across this plate? It should be constant, right? The pressure acting on this should be constant because it is a horizontal plate, submerged horizontal plate. So whatever be the height of the fluid it is inside. So let's say it is has a height h. So all the points on this plate are same height below the free surface. So the pressure at every point should be equal. So there's an equal uniform distribution of pressure across this plate. Now what is happening is that we are rotating along vertical axis. So if it rotates along vertical axis, every point on this plate still seems like stays at the same depth, right? Irrespective of this rotation, the points on the plate are staying at the same depth. Hmm. So there will be some viscous stresses acting on this due to this movement, but otherwise the pressure forces will be same. There will be no change in the pressure force, right?
Yes, sir.
So here the pressure force will not change. So the earlier the it was calculated as Fr, later also this will be Fr. But will the stress be same? Can you answer that question? Will the stress on acting on that horizontal plate will it be same if it is rotating?
So the stress may be vary because the pressure, the force will also act on the sideways because that is
Yes.
rotating.
So tangential stress
Yes, yes,
components will also be there, right?
yes, yes,
That arises from the viscous stresses, right? Hmm. But it is not asking really about pressure here. It is asking about hydrostatic force. So hydrostatic force should include those tangential stresses also, right? Because
yes,
those are
yes,
also hydrostatic, those also contribute to the hydrostatic forces. Correct.
yes, sir.
Hmm. So why are we still saying that the force will be Fr only, despite there are tangential stresses acting on the plate? Why are we still saying the hydrostatic force will be Fr, will not change?
but sir, because the plate is not moving, I mean, it is at a constant, at a constant place. That is
But
what.
it is rotating, right? It is
Yes, yes,
rotating. Hmm. So, so you are in the correct path. Since the plate is not like moving, its centroid is not changing its position. It is just rotating at its own place. So, at some portions there will be some viscous stresses, the others there will be some other viscous stresses, and they will cancel out. So, like if I see from the top, so let it this for simplicity I am drawing circular. It may not be circular as well, but it is rotating about its centroid that is mentioned, hmm, passing through its centroid. So if it is rotating along the centroid, maybe let's say uh, at this line, hmm, at this line it is rotating like this, so the viscous stresses should act in this way, correct? But
yes,
at this side, the viscous forces, stresses will act exactly opposite. So when you calculate the net force, this will cancel out. And the net hydrostatic force, there will be no tangential component to the net hydrostatic force, and there will only be the FR component. Hmm. What would happen if we would have like moved this plate along a tangential direction, along the horizontal direction? What would have happened? If it is translation instead of rotation, will the hydrostatic force be different or same?
it will be different, sir.
It will be different because there will be some tangential stresses acting on the surface of the plate, and the combination of those tangential stresses will not be zero. It will be non-zero component. Hmm. So that's what we like did while we were calculating shear stress of wall. I think like 2 weeks back we were calculating shear stress of wall. So there we were trying to calculate the hydrostatic forces due to the tangential component. So like that we have to keep in mind. So if it is submerged and it is we are like moving this plate uh, in the horizontal direction, then there will definitely be pressure. There will be definitely pressure. Along with that, there also will be tangential stresses which will be acting on this plate. So there will be a mm, mm, resultant hydrostatic force which is not solely due to pressure. There are tangential components as well. So, so this is the explanation that is given here. So there will be no change in hydrostatic force on this. Okay. Let me know one thing. Do you get these slides? Like, are these slides shared with you?
Yes, sir. At
Hmm.
the
It is accessible to
web,
you, right?
yes, sir. Similar at the website.
Okay, that's great. All right. So we move on to the next question. So this is a numerical question. This you will have to solve. So let's read what this question is saying. The gate AB has length L, width V into the paper. So okay, so this is like a three-dimensional thing, but only two dimensions are mentioned. So there is a width B which is into the paper, and it is hinged at B. Okay, so this is hinged here, hinged here. And this has negligible weight. Okay, the liquid level H remains at the top of the gate for an angle for any angle theta. Find the analytic expression for the force P. Okay, so the force P is acting here as mentioned in the figure. Force P is acting here, which is perpendicular to AB, and this is required to keep the gate in equilibrium in the figure below. So what is happening basically is there is a gate, and like one side there is water. Hmm. So what will happen? There will be pressure, right? Pressure on this gate, and uh, whatever be the pressure, there will be a resultant force due to this pressure acting on a very specific point, which is the center of pressure, right? As we have previously discussed. So there will be some resultant force, let's say Fr. some resultant force acting due to the weight of this weight or the pressure due to this the water. Hmm. So there will be some force acting. Now to counter that force, some other force, externally applied force P is being used. Maybe it is like tied to a chain or something. So something is trying to keep the water on the one side of this gate, and so that this gate does not fall off the hinge. Okay. So the situation is clear, right?
Yes, sir.
Hmm. So what we are asked is, we are asked to find this P, force P. So can you tell me how you will proceed to do this? So you will
Sir,
have to find.
we
Yeah.
will
Okay.
it is given at an angle, so we will uh, conserve the moment and then calculate the forces for each
Correct.
of the components and then
Hmm. So you have to find two things. So what, like, let's say this length is something. Hmm. Let's say this length is x0. We were using this x0 notation. Hmm. So you have to find both this x0 and this x1. If you find that, you can easily do this. So P into L. So this whole length is AB length is, I think, given as L. No? Huh. So AB has length L. That's the first thing. So P into L, this will be equal to FR into X. So from there you can find P. So for that you need to find both FR and X. So what I like personally prefer is using this the integration. So Fr, this is the resultant force, right? So if you just integrate from 0 to L, you should be able to get Fr. So for that you need to know the pressure. Okay, the P, already there is a P. So I will for this particular question I will use small p. Do not confuse between this P and the pressure P. Okay. So this is the relation. Now obviously the pressure varies, right, with point to point. From this, but every particular point, pressure is varying. So you have to find like total pressure. Hmm. Is that right?
yes, sir.
Hmm. You have to find the total pressure. So what is P of X? Can you like describe this function to me? So if I like, or at a particular, if I move x distance from B, what is the pressure at this particular point? So
So we
this,
rho
tell me.
g at the if we take the component along x and in the sine and cos, so rho g x cancel out.
You okay? Yes, definitely. But you don't need to do that sine and cos. That's why actually we are like taken the perpendicular component, na? Because pressure we know it always acts perpendicular to a surface. So you don't need to take perpendicular component. You just need to find this height. This height you need to. Force component you need not to take. So if this is x, then what is this height?
H minus x.
This is x sine theta, right? This particular.
Yes,
So this is B. Let's say I am assigning A, B is there. So let this point is C, and this is D. So I have assigned BC this length as x. Hmm. So my length of CD, this length will be sine theta, x sine theta, right?
yes, sir.
This is x sine theta, and then what is my pressure? My pressure at this point, P of x, this whatever is my atmospheric pressure plus the weight of this much water. Hmm. So this is rho g
Yes,
h
yes.
minus x sine
So,
theta. Okay, we can put this here. We can put this here. So we have 0 to L, hmm, and this expression P atmosphere. We have to like there's a little bit writing here, but this is a pretty simple thing. Hmm, H minus x sine theta dx. Okay, yeah. So P atmosphere plus rho gh. This is constant. P atmosphere plus rho gh. This part is constant. So this will be the P atmosphere plus rho gh. This is there into L. Correct. Hmm?
yes, yes.
This is correct. Okay. Now minus this is rho g
Fuji,
sine theta is there, and now integration of x, right?
yes,
Integration
yes.
of x dx. What that will be? X square by 2.
Right, yes.
Correct. So this is 0 to L. So this is L square by 2. Hmm. Is that fine?
Yes, sir.
Okay. So we have done this, and one thing we have missed is B, because this width is B, and that will always be there because pressure into area is your force, right? So pressure we have given dx is one length, so it should be multiplied by another length to make it area. So this will be B into this. So everywhere we have to multiply B. Okay. So this we have got as FR. I will move to the next. So they have solved it in another way. Like we will see how they have done as well. Hmm. So let's finish what the way we were doing. Now we have to find out x0, right? X0 we have to find. So for x0, what we will do, we will just like do a force like moment balance, right? For x0, we have to do a moment balance. Hmm. Or we can actually uh, yeah, we can do a moment balance. Actually, we need not to find this as well. Fr into x0, this is the moment, right? So we could have just simply added a moment there. 0 to L x uh, p of x dx. So this itself would have given us the answer. But anyway, since we have already doing this, let's let's do it. So x p of x dx. This is our moment, right? 0
Yes,
to
sir.
L. This is our moment. This is equal to Fr x0. Uh, so we will put our expression of P. What is our expression of P? P atmosphere is there plus uh, rho g h minus x sine theta is there. This is to be. So I'm just calculating this part of the problem. Uh, so x coefficient is there for P atmosphere plus rho gh. We will just take that to one side. P atmosphere plus rho gh. Uh, okay, here also I have missed B. B is will be there. B, I will multiply B. So since this is x, this will be L square by 2 into B, and minus this is an x square term. So x into x. So there will be an x square term. So rho g and b is there, and sine theta obviously is there, and there will be an x square dx. So x square dx, the
Mm.
this will be L cube by 3. Right? It will is x square x cube by 3. and if you put the limits, it will be L cube by. Okay. So this is equal to FR into X0. So from here we can find out X0, or we can like do one thing. Since FR into X0 is equal to PL, so here we can simply put my right hand side as P into L. So if I just put here P into L, then I can bring L the other side. So here is P atmosphere plus rho gh L into D by 2 minus, so sine theta I think we can like substitute it. Hmm. So H is given and L is given, so H by L is sine theta, right? H by L is sine theta. So we can simply put here. Instead of sine theta, we can write H by L. So uh, this is again rho g H from that H by L B, and L, one L is cancelled from here and another is cancelled from H by L. So L by 3. Okay, this is equal to your P. Okay, so what I feel here, what they have done, they have not taken P atmosphere. They have taken P atmosphere as 0, if I can say. Yeah, so they have taken P atmosphere as 0. They have neglected it. Force acting on the gate is equal to the force due to pressure acting on centroid of AB. Hmm. So this they have calculated. So this is basically our first FR, what we have done. This, if I put sine theta, the value of sine theta here, we will get the same expression as this.
Yes, sir. It's the same
Yeah.
expression.
So means you can like do this also. Since this is linear, this will always be average of this. That's what they have done. But it is a much safer way to just like put your expression of Px. So what they have done, they have neglected P atmosphere. So if we neglect P atmosphere, we would get exactly this. And then they have calculated this. So F R into X0, that is F into YECP for them. So they have done that, and they have used an expression for this moment of inertia. We have not done that. We have simply like we have simply calculated the torque. That this you can do if you remember 1 by 12 P by L cube, or you can do in this way as well. So you should get the same answer. So if I put P atmosphere as 0, what they have done, you will see like I will have rho g h into L into B, hmm, and here is half minus one third. Hmm. So half minus one third, if you do, what this will give you? This will give you 1 by 6, right?
Yes, sir.
Hmm. So this will give you 1 by 6. So you will get the same answer in both ways. Uh, that's what they have got here. So here also they have done the same thing. So they have, what they have used is the expression for moment of inertia. So oh, rho g sine theta into moment of inertia. Uh, so since the whole force is acting on that plate, so moment of inertia about the this the point at the bottom will be 1 by 12 PL cube. So from there they have calculated this YCP, and using this YCP again they have done now like moment balance, and they have calculated this. So whichever way you feel more comfortable, uh, we can do. But like either of the way, if you have any doubt, you can ask me. Is it clear how they have done and how like I have solved right now?
Sir, how they have done it is not clear to me.
Okay. So how they have done, let's investigate that as well, because like their concept is also very valid. So you should be able to understand how others are solving problems as well. So how they have done is basically they have calculated the force first. Hmm. So force, they have used a formula. So rho g h by 2 lb. So lb is area, and rho g h by 2 is basically the pressure at this halfway point. So this formula you can use if the pressure is varying linearly. So if the pressure is varying linearly and you are measuring pressure at the centroid, and there are many assumptions to using this. One, pressure varies linearly. Second, your geometry is symmetric. Hmm. Symmetry. There must be an inherent symmetry since this is a plate. The top portion and the bottom portion are symmetrical. If it were a square, if it were a circle, then also this would be valid. But like if it would have been something like a triangle, so maybe like at the top portion the area is less and the bottom portion the area is more, then this would have not worked. Instead, you would have, instead of h by 2, you would have had to put the centroid. The centroid of that particular geometry. Hmm. So this, for calculating centroid, what you have to do is basically integrate this. So what we have done and what they have done is basically the same for calculating the force. Okay, so up to this much is clear.
Yes, sir.
Huh. So they have got the force. So they have got Fr. What we have calculated as Fr, they have got. Now what they are doing, they are like taking some YCP and rho g sine theta into IXX. So what is rho g sine theta into IXX? Let me just draw this particular figure here. Hmm. So rho g into sine theta. Hmm. So rho g is acting this way. Rho g sine theta is acting this way. Okay, this is fine.
Yes, sir.
Hmm. This is fine. So IXX is the moment of inertia. So 1 by 12 BL cube. So 1 by 12 BL cube is from the center, right? If I
Yes, sir.
remember correctly, 1 by 12 BL cube is from the center. And they have done the same, like same thing, like moment using this force and YCP. Let me do it in my a little bit. F is the force acting this way, and YCP should be this. Okay, yes, yes. So whatever is our x0, that is only their YCP. Hmm. Yeah, they have not attached a figure. That's why it's difficult for me to understand which one they have taken YCP. F here is there. This is YCP. Hmm. This length is YCP, and what they have done is equated with the moment generated by the like water here. Hmm. So rho g, uh, so rho g is basically force per unit volume, right? Hmm. And if you multiply this with the moment of inertia, if you multiply this with moment of inertia, you should get, yeah, you should get force. You should get moment. So this is your moment. So the sine theta component is coming because I am not taking the I am taking force from this component. So whatever the like weight of the fluid is there, I am taking a component force uh, this side. So I am equating both of them, and I am getting YCP. So they have balanced the force, but they have just used a different concept. They have used the concept of moment of inertia. So there is a force is acting, and like if I want to calculate the torque on that, then I can use the moment of inertia, right? So like this is I alpha basically. Hmm. I alpha is your means torque will be I alpha, right? So same concept that they have used. Okay, hello.
Yes, sir.
So from that they have calculated this YCP. YCP F would act at a distance of x minus L by 2. Okay, so this is L by 2 is this point, L by 2 minus YCP. Okay, now they have not used this as Y. Okay, let me do one thing. Let me create a this uh, slide here where I can discuss this. Just wait a second. Hmm. Yeah, this is point A. Hmm. And this length is H, this length is H, this length is L. Okay. So what they have done here basically, first of all, they have calculated the force which is acting on this plate. That we have also done. So the force expression is rho g h L b by 2. Rho g h L b by 2. Well, this is dimensionally satisfying. So rho g is the is force per unit volume, and HLB has units of dimensions of volume. Now, what they want to know is where this force is acting. So that is very much required to like finally do the torque balance. So what they have done is actually use the center point. So uh, if I have the center point, then uh, like let's say YCP is my uh, distance away from the center point. The center of pressure is a little bit away from the this centroid at a distance of YCP. Hmm. So if that is the case, then my force into YCP, uh, my force into YCP should be equal uh, to the whatever the moment of inertia I have at this point, hmm, into the forces acting due to this pressure, because the this YCP is basically my torque acting at if I measure it from my centroid, whatever the torque is acting, that is F into YCP. So the same should be reflected if I take the pressure acting from the water. So the pressure from the water, for the pressure from the water, I am introducing this rho g sine theta. So sine theta is uh, basically coming to uh, for the directional purpose. So rho g will be acting. Mm, yes. If I am talking about pressure, then rho g would have been acting along the surface, right? Along the surface. But here I am talking about the like the weight of this fluid, whatever is here. I am talking about that. So rho g sine theta is there, and uh, this mm, this is multiplied with my moment of inertia. Mm. So moment of inertia across this centroid, this is 1 by 12 dLp. So from there, they have calculated this YC. From here, you can calculate YC. So this is the distance from the centroid, where your center of pressure is located. We know it will be downwards. Why it will be downwards? Because the pressure is more towards the bottom. So this will be downwards. So this could have been upwards as well. Because it is actually not giving me any idea about which direction YCP will be, just giving me the distance YCP from the center. You will get an expression. You will get an expression. We got an expression of YCP. Now they have changed their. Oh, sorry. Hmm. So now they have changed their point from where they are measuring. They have changed their point to B. Why they have changed their point to B? Because if you draw a free body diagram, there will be this force that is acting at this YCP location. Hmm. So YCP is this basically from centroid. This distance is YCP. This force is acting here. There is P that we have to calculate. Hmm. P this is acting here, and there is some force acting on B as well. There should be some force acting on B as well. Hmm. So we don't know the value of this force. We don't know anything about this force. What we know, this force is basically keeping this B point fixed, because we know this is the hinge, so this will not move. So there will be some force transmitted through this bit, through this hinge as well. Hmm. Till now, whatever calculations we have done, we have ignored this P and this FP. Hmm. We have only focused on the forces due to the hydrostatics of the water. Hmm. With the forces or the moments due to statics of the water. So that's why we could get away by considering the centroid. Now we are considering this point because we want to make sure that the moment applied by this FP will be zero. So that only we can make sure if we are measuring the moments from the point B. So from point B, moment due to FB is zero. Moment due to this F is basically F into L by 2 minus YC, right? Because that's the distance from point B. L
Yes.
by 2 minus
Yes,
YC.
sir.
This I am multiplying with P into L. Okay. This I am multiplying with P into L. If now you can, like, we have to find P. So they have, this is the method that they have followed. Hmm. So like I guess this method they have followed because it fits very well with the formulas that are generally used, like shortcut formulas that generally using this moment of inertia and all. Hmm. Otherwise, like if you want to follow through like basic concepts, I think you can use the method that we just discussed using integration. Hmm. So using integration, you just have to like follow the first principles, the basic principles of force application. Wherever uh, means, there are two things basically. One is force balance, one is moment balance. If you do both those things, then you will get your answer very clearly. Okay. Hmm. Uh, is this question clear? Like, will you be
Yes.
able to solve this question?
Yes, sir.
Okay. All right. Then I'm moving to the next question. So here also they have like it's a very similar kind of a question. So this is also numeric question. A tank is given and this has a 4 centimeter plug. So this is circular. So I think you know this kind of representations, right? So this is basically if you are viewing from this angle, you will see a circle. Hmm.
Yes, sir.
So this plug is used. Uh, So plug is used to keep this water inside. Now, if the pressure is increased, so if how are we increasing the pressure? If like this H height is increasing, then the pressure will increase, and after a certain height, this plug will fall off. So when this plug will fall off, it is given that if the hydrostatic force on this plug reaches 25 kN. So the force acting on this plug has been given. So we have to find out the reading on the manometer on the other side. So both those concepts of manometer and this hydrostatic pressure, both of them are used here. So can you tell me how will you approach this problem?
So say we will calculate the force at a distance of h, capital H.
Hmm.
Um, if the plug it is given the force required, if it is above than 25 Newton, the plug will open up. So
Yeah. So force you can calculate using the centroid because this is a circle. So you will find it a little bit difficult. Wait, someone is here, I guess. So you can calculate the force here, like you using the centroid rule. You will find it a little bit difficult if you want to use the integration because the shape is circular. So
yes,
for the force, what you will ideally have to do is do this P pressure into dA, where you integrate over the area of the circle, right? Hmm.
yes, sir.
Uh, now the like you can means ideally do this. It won't be a means impossible task to do this, but like means there is probably an easier method if you just use the like centroid rule and like whatever the force acting on the centroid, you take the pressure as well. Hmm. So basically, the concept here is if this is equal to this P dot dA is the force, right? So if this is equal to some equivalent pressure into your area, hmm, so then this equivalent pressure will be the pressure at the center. Hmm. So since this is linearly varying, the equivalent pressure will be the pressure at the center. So, like if I do that, then what I have to do? Let uh, so I have to calculate this height, this particular height, right? H minus d by two. So d by two is this. This length is d by two. I want to find the height. Hmm. This is 50 degrees is given. So this is d by two sine theta. So I am taking this 50 degrees. So this is my height, right? Hmm. So, what is the pressure at this particular point? I'll take the pressure at this particular point. Since at the end of the day, I have to balance the pressures. Hmm. So, this is uh, so the pressure at this point is P atmosphere plus rho G, G of water, sorry, rho of water. So, rho G H minus d by 2 sine theta. That is the pressure at this particular point. So let me start naming this point. Okay, let me name this point as A, and this point as B, and this point as C. So this is PC, pressure at C, right? P atmosphere plus rho G uh, H minus d by 2 sine theta. What about pressure at B? So let me take this as small l, like just for notation purposes. So here uh, you will see that. rho g, so this is rho of water into g plus h into h plus small l. This is equal to rho of mercury into g into small h. Is this correct?
Yes, sir.
Hmm. This treatment is correct, right? Hmm. Because we have to find small h, so we must have some way to relate it to our capital H. Because like whatever force we calculate on this particular uh, this this particular plug, this will be related to our capital H. Hmm. So there must be a way to relate this small h and capital H. So now we will just focus on calculating the force on this. So this is the pressure we have got on point C. Hmm. So what will be the force? Force on this plug. Force on this plug is pressure at point C into area.
Yes,
Area of this particular force. So that is pi d square by 4. This force F is given as 25 Newton. Right?
yes, sir.
Hmm. So this is given. The small capital D. D is given. You know P atmosphere, you know rho water, you know G. Capital H is not given. Capital H is your question mark. Small capital D you have theta you have. Hmm. So theta you have, P you have. What you can do is from here you can calculate your capital H. Correct. That is just an algebraic exercise. Hmm. It should not be a problem, right?
Yes, sir.
Okay. If there is any problem in understanding, please let me know. Okay. From here, after calculating capital H, what we will do? Can you tell me?
Yes, sir. It's easy. We will put that in rho g h plus L equation, and
Yeah.
then we will get the value of h, small h, because the
Hmm.
L is given to CCM.
Yes. Hmm. That makes sense. Absolutely. Let's see what solution is offered here. For some reason, they are excluding your P atmosphere. So you can also do that. Exclude P atmosphere. I guess like rho g's value will be much larger in case. Hmm. Rho gh will be much larger than P atmosphere. Many a times that is not the case though. The atmosphere is not a like very negligible value. But here, I think in almost all the problems they're excluding the atmosphere. So yeah, they have used this. They have calculated Z as 2.03. I don't know from where did they get this. Oh, yeah, by equating this. Yeah. So Z they have calculated from here. So H they have calculated from this Z. So that's what we had done as well, right? That's what we had done as well. So this H minus d by 2 sine theta that they have taken as Z, and from that they have calculated this H, and then they have used this equation. Here they have included P0, but P0 here does not make any difference because it will cancel out. So I don't know what's going on. Okay, all right. Let's look at the next question. Here also, I think very similar, very similar. So, can you tell me what to do here?
Yes, sir. We will calculate the force at the distance from B at the point P. It is given,
Mm-hmm. Yeah.
which is 5 centimeter, 5 meter 5 meter below the atmospheric pressure.
Hmm. Yeah. So here also you have to just to find this P at equilibrium. This like let this 3 centimeter. Let me call this as L, and let me call this as H. So P into L, this will be equal to your torque due to the pressure. So integration some like whatever this is area, because this is not plane, so this is just integration area into. mm, Let me still call this height as y. So y p into d. So you can means calculate this dA. So one way to do this by integration only. So that you don't have to memorize unnecessary formulas. So you can calculate this dA. So let's say you want to find this pressure as a function of y. You can find. That is not a problem. Like this is y. So at any y you can find pressure. What's challenging is finding dA.
The,
So that also you can do. That also you can do. So. Uh, so let us consider this as your dy. What you have to do is basically calculate this area. This will be your dA. So how to do that? This L is the diameter. L is the radius. Sorry, L is the radius. Right. Capital L is the radius of this. So this you have to find the this length. Hmm. So let this be theta. So theta we can calculate later. So if this is theta, then your this is this half length is L cos theta, right? This is L cos theta. This is a half length. So your dA will be 2L cos theta into dy, right? Dy is the thickness. 2L cos theta is the length of this. Hmm. Now cos theta also you can put. How? You know this is y. Hmm. And your this is L. Hmm. So cos theta will be nothing but uh, cos theta will be this by so root over L square minus y square. You have to do some integration uh, divided by L. Hmm. So your L will cancel. This is root over L square by y square. Hmm. 2 into this into dy. So you will put it here. Pressure you have to calculate. So pressure at point Y is basically mm, pressure at point Y is pure atmosphere. I think we have to neglect here anyway. So this is rho G H plus L minus Y. So I'll just put it here. So this is Y into rho G H plus L minus Y. dA I will put from this side. This is 2 into root over L square minus y square into dy. Okay, now you have to do some integration. These integrations are not very difficult, so two will do this. So this is from 0 to L. So y will vary from 0 to L. So this is 2 rho g h plus L. Let me like separate it like this. H plus L is y into 0 to L, y into root over L square minus y square dy. Do you remember how to solve this integration? Just let me ask you this. You might have done this in school, your class 11, 12. You have definitely done this. So if it is in this format, then you can like basically like just This is a method of substitution. Hmm. You would take this as some random variable. Let's say take this as q. Hmm. So if you substitute this as q, then you would minus 2y dy. This will be dq.
Yes, sir.
Yeah. So you can like use this to solve calculate this integral, and again you can uh, you will have another integral here minus 2 rho g integration y square root over L square minus y square. Okay. How to solve this equation? How to calculate this integral? Do you remember?
We will take root over of square minus y square as some constant and square that now.
Hmm. Hmm. So, like uh, here, I think the better way to will be to do by parts once. If you just do by parts once, then you will like get this. Means anyway, you are doing this integral. Like you are already
Yes,
doing this integral. Hmm. Correct. We are
yes,
already solving for this integral. So this is basically this is if you take this as easily integrable one. Hmm. So easily integrable one like so the let me take this as first function and into y will be my second function.
same concept.
Then you can easily do just one. If you do by parts, you will easily get this. Okay, you can do this. Means this way, I think they have like given some formula. Hmm. So one thing, the way you can do this very easily, like if you are appearing for some competitive exams like GATE and all, then you like seeing this problem, you will know what you have to exactly memorize. What you have to memorize? You have to memorize this if you want to avoid doing this particular integral. This is not impossible problem to solve. So, like away from your competitive exams, you can easily do this problem by solving this integral. You will have tools for solving integrals as well. Like if you are becoming an engineer, you will have access to various softwares like Mathematica or MATLAB, which can instantly give you the results of this kind of integrals. Other than that, for competitive exams, you will have to memorize. Like if you want to do it in a quick time, hmm, not trying to do those integrals, you have to memorize this. Location of centroid of semicircle from your base. So if you know this, then this is extremely easy. Hmm. So what is this saying? This is saying that if you have a semicircle of like radius L, then your location of centroid of this semicircle from this base, this is 4 by 3 pi into d. Okay. So if you know that, then it is very easy. Hmm. Then what is your force acting on this? The force acting on this particular thing is nothing but H plus L minus this 4 3 by pi L d into rho g into your area. Area is pi d square by 8, L square by 8. This is also L because diameter is L. Right. Understood?
Yes, sir.
Yeah. So if you know this formula, then you can easily solve this. Then you know this centroid of the semicircle from base. You know the uh, then you will know the force acting on this. So this is the force acting on this. So this is equal to F. Hmm. Now, from there you can like easily find out uh, this relation, this particular. Okay, okay. Is the problem this how to do this problem? Is it clear?
Yes, sir.
Okay. If you have any doubt, let just ask me. Like from the previous classes as well. I always say this. So from the previous classes as well, if you have any doubt, discuss. Okay. So now we move to buoyancy. So here is uh, yeah. So the question is the iceberg shown in the below figure can be idealized as a cube of length L, side length L. Okay. So if seawater is denoted as S is equal to 1 and has S is equal to 0.88, iceberg has S is equal to 0.88. So what is S?
Specific
Hmm,
gravity.
Yeah. So this is basically the density with respect to water. Which among the below statements about its stability is true? So can you tell me this? So what is G? What is M? What is B?
So M is the meta center, G is the center of gravity, and B is Buoyancy.
B is center of buoyancy.
Yes, sir.
Hmm, Okay. Uh, so all right. So can like from the surface of the uh, from the surface of this water. hmm, So what is the height? What is the depth of the center of buoyancy? Dimensions are given as L and H. So what will be the depth if it is in the stable position? If it is in the position as shown, then this will be H by 2, right?
Yes, sir.
H by 2. Because what is center of buoyancy? This is basically if the like solid body is uniform, then the center of body buoyancy will be the uh, centroid of the submerged portion. And if the body is uniform, then G will be the centroid of the whole, the complete, uh, mm, mm, complete body. So which of the following statements are true? The distance between the distance mg is greater than 0, then the iceberg is stable. Mg is less than 0, iceberg is stable. Mg is greater than 0, iceberg unstable. And mg less than 0, iceberg unstable. So there are four options. Hmm. So let's first see what happens if it tilts slightly. So there are two forces acting on this, right? Two forces acting on this. One is at G, one is at B. Hmm. Uh, so this G force will be acting this way, and this will be acting. Center of buoyancy will be acting. Buoyancy force will be acting this way, right? The way I have drawn is this stable or unstable?
Sir, if the meta center is above the G, it will be stable.
Okay. If a metastable is above G, it will be stable.
Yes, sir.
Can you explain me more?
Because if we uh, provide a torque, it will
Hmm.
give a counter torque in the opposite direction.
Hmm. That is correct. Hmm. So I have drawn like in the green colored pen. You can see I have drawn this a figure. Hmm. So can you tell me in this particular figure is the meta center above G or below G?
Meta center is below G, sir.
In this it is below G, right?
Yes, sir.
That's why it is this is unstable, right?
Yes, sir.
This is unstable. Because the torque that you can see is this torque will actually further submerge this means, enhance this perturbation. If like for a ship, so what happens? The center of gravity is much lower. So center of gravity is much lower. So if you slightly tilt this, if you slightly tilt this, then there will be a resultant torque means acting definitely. So the center of gravity will be here. Center of buoyancy will be above. So this will try to make it come back in its original position. So that means this is stable. And meta center, the position of meta center is basically used to identify this. So here, this is basically the center line, and can you like give the definition of the meta center?
So the reaction forces will intersect with the.
No, reaction forces I understand, but like how do you find point M? How do you find point M?
So that metacentric height or only the point M.
Hmm?
So metacentric height or only the point M. Because if we have to find the point M, the reaction
Hmm.
forces which will intersect with the, if we give the torque, it will react at 2 points where it will
Hmm.
coincide, that will be the.
So if I draw a center line,
Yes,
and
sir.
this is the buoyancy force where it intersects, that point is
Metacentric point.
hmm. Okay. So mg, if it is greater than zero, then the iceberg is stable in this case, right? Hmm. Okay. Uh, that is the correct answer. So if it is here they have done calculation and all, but I like in general also, like if mg is uh, this is meta center is above, then it is stable. So that means like whenever there is a small perturbation to the floating object, then whatever the torque is generated, that will be against the perturbation. It will try to reduce the perturbation, and the floating object will come back to its original state. Okay. All right. So here option A is correct. If mg is greater than zero, iceberg will be stable. Okay. Mm. So here also a very similar like buoyancy related question is there, is not stability related. So here uniform block of steel, its specific gravity is given. This solid specific gravity is given. Mercury specific gravity is given, and this block is basically lighter than mercury and heavier than water. Its specific gravity lies in between. So you have to find how much portion is inside water, how much portion is inside mercury. So can you do that? So what will you do? You will like take the steel block and you'll do a force balance. Basically, this is nothing but a force balance. So there is one force is gravity. Hmm. So this is whatever is the steel block. So density of the steel block, and into G into the volume of the steel block, right? Rho into G into the volume of the steel block. Hmm. So let me just denote this as capital V. So this is there, and there will be two buoyancy forces. One buoyancy force will be due to the water portion, right? So water portion buoyancy will be rho into W, density of water, G. Hmm. So this is not the total volume. How much portion of this it is? This is A into A plus A by A plus B. Okay. Is this? Do you understand why I have done this A by A plus B? So
Sir,
this is the.
why A plus B?
Hmm?
That A by A plus B. Why A by A plus B? That I don't understand.
Sorry, I couldn't hear you. Can you speak again?
Sir, why we have done A by A plus B?
Because, like, let's say the volume is V, capital V. So, what is the like fraction which is above inside water? So, if I take the length, if I just take the length, so let the height and breadth of the steel block be H and B. So, what is the volume of this? So, volume is H into B into A plus B.
Yes,
That
sir.
is
Yes, sir.
correct. Hmm. So what is the volume inside water? Volume inside water is H into B into A. Correct.
Yes, sir.
H into B into A. So what I have done is I have just calculated the volume inside the steel block using V, because I have used V as my symbol. So this is V1. So this is this. So if I just simply like divide by A plus B and multiply by A plus B, this will be equal to V into A by A plus B. Okay, is this
Yes, sir.
clear? Hmm.
Yes, sir.
Okay. So another buoyancy force will be there, which will be rho into Hg into G into V into B by A plus B.
We will.
Right. Hmm.
Yes,
So
sir.
I will just balance this out. Hmm. So uh, rho s into so g's will cancel, all g will cancel, right? If I do a force balance, all g will cancel. And also, like, if I divide by rho water, then this will be basically of uh, s of steel, specific gravity of steel, into v. This is equal to g I have cancelled, rho water I have taken common, so this is v, a plus b plus S of mercury to V to V by A plus B. Okay.
Yes, sir.
Hmm. Okay. So we can easily solve this. So V, all the V will cancel because V is irrelevant, right? Here we only need the ratio. Hmm. So still this I will put specific gravity I will put as 7.85. And let me just take A plus B this side. So and this side it will be A plus 13.56 into B. Correct.
Sir.
Hmm. So from here you can actually find out effect. How? You can do this, right?
Yes, sir. Yes.
So this will be 13.56 minus 7.85 divided by 6.85. Whatever is the answer. Looks like C. Let me check.
Yes, sir.
Yeah,
7.8.
this is C. Okay. So this was the last question for this assignment. If you have any doubt, you can ask, like related to this topic. Do you have any doubt?
No, sir. But sir, is there no question regarding the fluid under rigid body motion, because we have already also covered that in this week.
Fluid under rigid body motion.
Yes, sir.
Okay. I'll just see which week was it covered.
So it's the same week 4.
Week 4. Okay, I have not received any questions from there. Okay, I will try to include that in the next segment. Okay.
Yeah, thank you,
So,
sir.
hmm, right. Any other topic that is like being missed, you can tell. I have noted fluid on the rigid body motion. If there
No,
is
sir.
any other topic. Okay. All right, then I'm ending this session.
Yes, sir. Thank you,
Okay.
sir.
Thank you.